In this video, we'll build intuition for reinforcement learning by training a Q-learning agent from scratch. We'll use a simple game called Catch, where a basket tries to catch falling fruit. Step by step, we'll see how the environment is defined, how Q values are learned, how experience replay helps, and how the training loop works. And yes, there will be quizzes in between, so you can check your understanding as we go. Let's start with the problem itself. In Catch, the environment is a simple 10 by 10 grid. A single fruit appears at the top in a random column and falls downward over time. At the bottom there is a basket that is 3 cells wide and can move only left or right across the last row. The agent's job is very straightforward. Move the basket so that it catches the fruit before it reaches the bottom. It's a small game, but it captures the core idea of reinforcement learning beautifully. Now let's translate the game into reinforcement learning language. The agent is the basket controller. The environment is the grid, the fruit, and the game rules. The state is represented as a 3-value tuple: fruit row position, fruit column position, and basket column position. The action space has just 3 choices: move left, move right, or stay still. The reward signal is also simple: +1 if the fruit is caught, -1 if it is missed, and 0 while the fruit is still falling. This reward structure tells the agent what success looks like, without explicitly telling it how to play. Q-learning is all about estimating Q values. A Q value tells us how useful a particular action is in a particular state, based on the future rewards we expect to get. So instead of memorizing a direct policy first, the agent learns numbers that score each action. Once it has those scores, it can choose the action with the highest Q value. In simple words, the agent keeps asking, from this situation, which move is likely to help me most in the long run? This article also places Q-learning inside the bigger reinforcement learning landscape. First, it is value-based because it learns action values instead of storing an explicit policy. Second, it is model-free because it does not build a predictive model of the environment, it simply learns from interaction. Third, it is off-policy, which means it can improve its estimates using experiences generated by a behavior policy that may include exploration. And finally, it uses temporal difference learning, so it updates estimates during the game instead of waiting only for the final outcome. Now that we've covered Catch and Q-learning, let's test what we've learned so far. Here's quiz number 1. See if you can get it right. Question 1. In the Catch game, what does the agent control? The correct answer is the basket. The agent controls the basket and tries to move it so the falling fruit is caught. Question 2. Which of the following is the correct state representation described in the article? The correct answer is fruit row, fruit column, basket column. The environment state is defined as a 3-dimensional tuple containing fruit row position, fruit column position, and basket column position. Question 3. Why is Q-learning called value-based in this example? The correct answer is it learns a value for each state-action pair. Q-learning learns Q values, which estimate how useful each action is in each state. A very important part of this setup is the experience replay buffer. Instead of learning only from the latest move, the agent stores many past transitions and reuses them. Each transition contains the current state, the action taken, the reward received, the next state, and whether the episode is done. During training, random samples are drawn from this memory. This breaks up correlations between consecutive steps and makes learning more stable. It also improves sample efficiency, which means the agent can learn more from the same amount of gameplay. The environment code is split into a few clear functions. The act function takes an action from the agent, updates the environment state, calculates the reward, and checks whether the game is over. Then the observe function redraws the 10 by 10 grid, so the current state can be represented as pixels. There is also a reset function, which starts a fresh game by placing the fruit at the top and randomly initializing the fruit and basket positions. Since the basket is 3 cells wide, its center cannot start at the extreme edges. In the replay buffer implementation, experiences are stored in a simple Python list with a maximum size. Once the buffer becomes full, new experiences push out the oldest ones. That keeps memory bounded while still preserving a useful training history. The key helper method is the one that builds a queue learning batch. It randomly selects stored experiences, prepares the current states as model inputs, and creates target queue values for training. This method is specific to queue learning because the targets depend on the queue update rule. Now that we've covered replay and environment, let's test what we've learned so far.
Here's quiz number 2. See if you can get it right.
Question 1. What does an experience in the replay buffer contain? The correct answer is state, action, next state, reward, and done signal. The article defines an experience as the state-action interaction plus reward, next state, and optional done flag. Question 2. What is the main purpose of random sampling from the replay buffer? The correct answer is to improve sample efficiency and training stability. Random sampling helps the model learn from diverse past experiences and reduces instability from highly correlated sequential data. Question 3. Which environment function is used to start a fresh game state? The correct answer is reset. The reset function reinitializes the fruit and basket positions and starts a new episode. Now let's move to the training file. The queue learning agent uses a neural network built in Keras. The input is the flattened grid state, basically the pixel representation of the board. Inside the network, there are two hidden layers. At the output, there are three values, one for each possible action: left, stay, and right. So the model takes the current game state and predicts how good each action is from that state. That prediction becomes the basis for both action selection and learning. During training, each epoch corresponds to one run of the catch game. The environment is reset, the agent starts acting, and every transition is stored in the replay buffer. After each action, a batch is sampled from memory and the model is trained on it. For choosing actions, the code uses an epsilon greedy strategy. Most of the time, the agent picks the action with the highest predicted queue value, but some of the time, around 10% in this article's example, it chooses a random action. This exploration is very important, because without it, the agent may never discover better strategies. Once training is complete, the saved model can be used for inference. At each time step, the current grid state is passed into the model. The model returns estimated queue values for the three actions. The action with the highest value is selected and sent to the environment. The environment then updates the state, returns the reward, and the new frame is drawn. If training has gone well, the basket will now move much more intelligently and catch the fruit more often. Now that we've covered training and inference, let's test what we've learned so far.
Here's quiz number 3. See if you can get it right.
Question 1. What does epsilon greedy mean in this training setup? The correct answer is the agent usually chooses the best known action but sometimes explores randomly. Epsilon greedy balances exploitation and exploration by choosing a random action with probability epsilon. Question 2. How many action values does the neural network output for the catch game? The correct answer is 3. The actions are left, stay, and right, so the model outputs 3 queue values. Question 3. During inference, how is the next action chosen? The correct answer is the action with the highest queue value. At inference time, the trained model predicts queue values, and the agent picks the action with the maximum value. That's the full walkthrough of training an RL agent from scratch using queue learning. If you understood this pipeline, you've already covered many of the most important ideas in practical reinforcement learning. Keep experimenting with the grid, rewards, epsilon, and model design, and you'll build even stronger intuition. See you in the next lesson.